Okay, so this is the base of our foot. The base of our foot is designed with the ankle joint in mind and is created pretty much to house the ankle joint. So as we can see here, this is the bottom of the base. The sketch here shows the dimensions of the base, and so the dimensions were dictated, roughly measured off of one of our group members' foot, and was designed to be big enough in order to fit the ankle joint. It has measurements roughly of double that of the ankle joint, so that the ankle joint will be able to fit comfortably on it. So it is 8 inches lengthwise here, along with a 4-inch diameter semicircle here and a 2.5 radius semicircle on the other side. Pretty much the curvature is just added here in order to replicate the shape of the foot better. So that sketch was created using a circle here, 2 lines, and then creating a curve on this side. The sketch was then extruded up with the length of 0.5, as that was the thickness of the wood in which we purchased to create this foot out of. The sketch seen right here is made of a circle and ellipse. The ellipse is created here in order to show us where the ankle joint will be placed. It is the same size of the ankle joint and therefore gives us an accurate measurement of pretty much where the ankle joint will be placed and how big it would be in comparison with the foot. Right here we see another plane is created. This plane will be used to create the sketch that will ultimately be made for the sides of the foot. So as we can see right here, this is the side of the foot. And this is the sketch that was used to create the sides of the foot. The sketch was first created using a circle up here, which is the diameter of the rod in which we are going to be sliding through that hole. It is raised 2 inches off of the foot, and that's because the location of the hole on our bottom ankle joint piece is 2 inches up. So after creating this hole, we created a 2-inch diameter circle around it, kind of just there to be put for stability, and we created 2 lines down, and we set the length down here to be 4 inches. And these measurements were kind of just eyeball to see what would fit with the foot, and the 4 inches here is kind of just to be able to encompass the ellipse here, just to create a better aesthetic. This was also extruded 0.5 at 0.5 inches because that was the thickness of the wood in which we had. So that feature was then mirrored across to be able to create structural supports that the rods will go through, as long as structural supports for the overall ankle joint. So this here is our top ankle joint. It is the main part that makes up our ankle joint system, which is a single axis ankle joint. This, along with the second ankle joint, will be combined together using a metal rod to create that single axis movement to allow the foot to account for more uneven surfaces. So to start off, this part was created using an ellipse. As seen here, this is the sketch for the ellipse. And just to mention that all measurements for this part were roughly measured using one of our group mates' ankle. So we took measurements of the rough estimates of the rough size of what it was, and we added around 1 inch just to assure for more stability and to just give more room for error. So once this ellipse was drawn onto our top plane, it was blind extruded 0.5 inches. This measurement of 0.5 inches was kind of just an eyeball to see around how big it would need to assure stability, to assure that it wouldn't really snap. So now we can see that there is a cylinder here. So the purpose of this cylinder is to house the pylon that would attach it to the rest of the leg. So this feature was created using a circle sketched onto the face of the extruded ellipse and then extruded upwards 3.5 inches. So the circle has a diameter of 2.6 inches, and that's due to the fact that the pylon has a diameter of 2 inches, and we wanted this to be bigger so a later cut would be able to be made into the cylinder to house the pylon. This was a blind extrusion up. So now we can see here there's another extrusion, and what was made was that another sketch was made onto the face of the ellipse that kind of just encompassed the shape in between the ellipse and the side of the cylinder, and it was extruded an extra 0.5 inches up. It was in a blind extrusion, and this extrusion was created due to the fact that this side of the ankle joint will be the side that hits the bumper, and that's kind of to restrict some motion for the ankle joint to assure that it isn't too wobbly and allows for better stability while walking. And that's the sketch you can see right there. And now a plane was created. So this plane was used to create this cylinder that has just appeared here. So on plane 2, a circle was drawn with a diameter of 2 inches. This was more of a relative measurement that was kind of created gauging on the size of the entire ankle joint. It was also the more favored size of some of ankle joints that are already on the market, and it was just a size that fit best with our metal rod that would be inserted through, which had a diameter of 0.5 inches. So this circle was created, and then it was extruded. It was a blind extrusion across, as you can see here. And it is extruded a total of 2.6 inches. So as you can see, it is the width of the cylinder and of the ellipse. The sketch can be seen right there. It has a diameter of 2 inches, and it was extruded across. So now we can see on top that there is a cut made. As mentioned earlier, this is where the pylon will be housed. So this cut was created by drawing a circle, sketching a circle on the top portion of the cylinder with a diameter of 2 inches. It was a blind extruded cut downwards then, and it was just extruded down enough that there was still enough stability in the middle of the part, and extruded down enough to be able to fit the pylon securely, with enough area for us to be able to apply glue to the area so that the pylon will stick in. So now we can see that another plane was created, and this is plane 3. This plane was used to create another cut as well. So this is the beginning of the cut that will be used for the second ankle joint to be attached to. This cut was created using a rectangle, or more so a square, of 2 inches on both sides, and it extruded up an inch, just enough to hit the halfway point of the circle. From there, another cut was made, and this cut was made by picking one of the sides of the earlier cylinder, the bottom cylinder here that was created using plane 2, and it was a cut made with a circle sketched on one of the faces with a diameter of 0.5 inches. This cut was a through-all cut, and it was a cut made in order to fit the pylon, it was made to fit the metal rod that would later be used to connect both ankle joints together. So lastly, we have the last cut. So this cut was to finish the cut and make it a rounded cut inside the first ankle joint, for there to be a rounded second ankle joint part to go inside to allow a movement along an axis. So this cut was made on the right plane. And it was a circle of 2 diameters, so mimicking the cylinder, and it was a mid-plane cut, extruded cut, that was 2 inches across, leaving some room on the sides for there to be thickness on the sides in order to house the ankle joint in the middle. So that is the total and final first portion of the ankle joint, and once again it was created in order to 1. House the pylon, 2. Be able to hit the bumper to ensure stability, and 3. Have an area to house the ankle joint, or the second part of the ankle joint, to allow rotational motion along an axis, and also have an area for the rod to go through to act as the axis. So this here is the bottom portion of the overall ankle joint. It is the bottom ankle joint and was created to fit in with the first part of the ankle joint. So therefore, all the dimensions of this ankle joint was made in accordance with the first ankle joint, meaning that all the dimensions were made so that it would fit into the cuts that were made into the first ankle joint. So first of all, we have the main cylinder of the ankle joint. This was created by sketching out a 2-inch diameter circle onto the front plane. Then extruded boss/base was used, and a mid-plane extrusion was made of a total of 2 inches. After that cylinder was made, a second cylinder was made using the same methods. So a circle was created, this time on the top plane. This circle had a diameter of 1 inch and was blind extruded down for a total of 2 inches. After that cylinder was created, we then made a cut through the main cylinder. This cut was created by sketching a circle onto one of the faces of the first cylinder and then using a through-all cut. The circle sketched had a diameter of 0.5 inches, and that was created due to the fact that the metal rod which we had, which would connect the 2 ankle joints together, had a diameter of 0.5 inches. So this part was made to be able to fit into the first ankle part and have the rod go through both of them in order to create a single axis system. So it was meant to be able to have the first ankle joint be able to rotate around this one.
This is the cage that holds the rack and pinion system, which acts as a friction-activated knee joint. On the front plane, 2 rectangles were created 3.4 inches apart. To do this, a center line down the y-axis of the origin was created. Left of the center line, a 3.4 by 5 inch rectangle was drawn. Using the Smart Dimension tool, it was automatically placed 3.4 inches from the mirrored side. The center of the vertical line was mated horizontally with the origin. The mirrored side was created with the mirror tool. It was extruded 4.5 inches back, a little longer than a typical knee, in order to allow the gear to move inside. Next, on the right side, a sketch of a circle was made with a diameter of 1 inch. The center was set 1 inch from the bottom and 2 inches from the back edge. The cut was then extruded through all. The circle wasn't drawn at the middle of the rectangle. It is closer to the back edge in order for the gear to have room to crawl forward inside. Next, a 0.5 by 0.5 inch square was drawn on the right block 0.75 inches from the bottom and extruded out 0.5 inches. Another Another 0.5 by 0.5 inch square was drawn on the inner surface of the extruded cube and then was extruded to the outer surface of the leftmost block. This completes the sketch for the cage that holds the rack and pinion system. This is the pinion in the rack and pinion system. It effectively acts like a knee in this design. To create this pinion, a 3-point arc with a radius of 2 inches was created. It was extruded back 3.38 inches, which is 0.02 inches smaller than the gap between the side pieces for clearance. This was approximately the size of a real knee and allowed for a circumference large enough to support many teeth of a reasonable size. A qualitative decision to put 20 teeth around a half circle was taken. It seemed this would be the optimal number of teeth to have the highest probability of catching the pinion in the rack after re-engaging without the teeth being too big or too small. Using the line segment function, a tooth Using the line segment function, a tooth in the shape of a trapezoid was created and mated with the half circle using coincident mates. The trapezoid was 0.25 inches tall, with the top base being 0.06 inches from the horizontal. The base was extruded up to the back surface of the half circle. The center of the bottom of the base is 6 degrees from the horizontal. The base was extruded up to the back surface of the half circle. The tooth was then circularly patterned 20 times around the half circle. The patterning came out a little weird, so a quick cut was made in order to return it to a half circle. Another cut was made to make the teeth flush against the front of the half circle. A rectangle was drawn on the front plane, and the edge was made coincident with the desired edge. This is the before and after. Many fillets with a radius of 0.3 inches was made in order to protect the teeth in case it clashed at the wrong angle with the rack. A sketch of a rectangle incorporating the entirety of the base of the half circle was created and extruded 1 inch below the half circle. From the front of the half circle, a rectangle 1.25 inches long and 0.25 inches tall was created at the base of the 1 inch extrusion. The base was extruded to the next surface. From the bottom of the piece, a cylinder with an outer radius of 1.8 inches and an inner radius of 1.6 inches was created. It was located with its center lined up with the half circle center and in the middle of the width of the rectangle shown. More fillets with a radius of 0.03 inches were made for aesthetic and durability. Finally, an H7 interference fit hole was created at the center of the half circle using the hole wizard with a radius of 0.5 inches. This concludes the pinion part review. This is the rack/top plate system that sits on top of the cage that houses the knee joint. This has gone through multiple iterations, which you can see as we run through the history tree. The first step is to make a 3.8 by 4.5 inch sketch on the top plate, extruding to a height of 2.5 inches from the midplane. From the midplane, create the rough dimensions for the teeth. The teeth are in the shape of a trapezoid. They are 0.25 inches tall with two bases of lengths 0.2 and 0.06 inches. The first tooth was created with a bottom corner coincident with the left edge of the plate. It was then linearly patterned across the plate 14 times. This number was calculated from the given number of teeth on the pinion, 20. Since the pinion has a diameter of 4 inches, it had a circumference of 4 pi inches. In a full circle, the pinion would have 40 teeth. A proportion can be set up with teeth per inch. The rack has a length of 4.5 inches, so there would be some number of teeth per 4.5 inches. 40 teeth divided by 4 pi inches times 4.5 inches yields approximately 14 teeth, the number of times the first tooth was linearly patterned. From the midplane, it was extruded to 3.4 inches, the distance between the side plates. Next, each tooth was filleted to a radius of 0.3 inches. This is to protect the teeth if the pinion came down at the wrong angle. A decision to change the top of the plate led to a 0.1 inch expansion on all sides of the teeth. This was done by using the Offset Entities tool. Additionally, 0.2 inches were added on the left and right sides of the piece. A sketch on the front of the piece was created and extruded to the back surface of the piece. This created a total width of 4.4 inches. This allowed the current top plate to span the entirety of the cage and sit flush against the outsides of the cage. Additionally, the 0.1 inch expansion on the top of the plate made the plate sturdier for the mounting of the shin and thigh brace. This concludes the top plate of the rack system.
So this is the part of our bottom pylon. The bottom pylon was created using the extrude thin function. So it was based off of a sketch of a circle of 2 inches. This 2 inches would be the outer diameter of this. The thin extrusion had a thickness of 0.1 inches and extruded a total of 10 inches midplane.
This is the top pylon. It was created with an inner diameter of 2 inches and was extruded from the midplane 10 inches. It has a thickness of 0.1 inches. A cut was made at the bottom in order to allow a clamp to actually squeeze the bottom of this. The way this cut was created was by making a sketch on the bottommost surface of this cylinder with 0.4 inches across from the center line. It had 2 arcs were created and 2 lines were drawn down the center, the inner and outer arc. These were made symmetrical with using the center line. This is a simple rod that was used for all of the holes in our project that required rotation of motion. It was 0.5 inches in diameter and it was extruded from the midplane 4.4 inches. This is the thigh holder, which was used to hold a non-amputee's leg. The first sketch was a center square that was made 6 inches by 12 inches. On this plane of that square, a 0.5 inch rectangle by 12 inch rectangle was created with the bottom coinciding with the top of that last rectangle. This is extruded back to the back plane of that rectangle. Next, a center line was made down the middle of the thigh plate with 0.5 holes cut 1 inch from either side and mirrored across. This is for straps to go through to strap in the thigh. The same thing was done on the shin plate. The holes were 0.5 inches in diameter and 1 inch away from either side. It was then mirrored across the center line to allow the shin to strap in.